All right, we have to really quickly talk about wave functions. So a guy named Schrödinger kind of came up with the Schrödinger equation. It's kind of how it works. You come up with a famous equation, you get to stamp your name on it. So in the Schrödinger equation, proposed what we call wave functions. And we used the Greek letter psi to represent these wave functions. And so it turns out he was talking specifically about electrons. And so we started realizing, more and more that even matter could be potentially having wave-like properties and stuff like that. And so he described electrons as having a wave-like motion or something like that. So still debatable what exactly this means, but what's nice is you can take the wave functions he was able to solve, and if you square them, it gives you a nice probability map of where you might find an electron. So, and if you look, what did I include in this section on your handout there? All the orbitals, the s orbital, the p orbital, the d orbital. If you solve Schrödinger's equation, so for an s orbital or a p orbital or a d orbital, that's where those shapes come from. It's the wave equations squared, the wave function squared, to give a probability map. And so if you want to look to like the 95% probability, those shapes are where you'd find the electron in those orbitals. So that's where they come from. They're solutions of the Schrödinger equation. And so he kind of ran with the idea that, everything's got some sort of wave-like behavior. We'll find out de Broglie played a role in this in a little bit. And that's as far as he went. You should just know there are wave functions. When you square these wave functions, it gives you a probability map of the volume in space where you might find an electron.